In this example, we are going to look at how to do a combined concept problem that also involves conservation of energy. So we have been given a car of mass m, and it's initially at rest at x equals 0 and t equals 0. Has a non-constant acceleration given by this function. A as a function of t is equal to c, a constant, times t. And it has that not until a time that we're given, but until a position x equals d. After that, it's going to travel down the frictionless hill of height h, and it's going to pass over a rough patch of length L and then coefficient of kinetic friction mu sub k, and it compresses a spring then with spring constant k. What is the maximum compression of the spring? So this is going to be basically two parts. We're going to have up on top of the hill, when we have this acceleration as a function of time, this will be 1D motion with non-constant acceleration, meaning that we're going to have to use calculus. We're going to have to know that the velocity as a function of time is the integral a dt, and because we're going to want to know the speed at a particular time, we're going to have to know at what time it gets to position x equals d. So we'll actually have to take another integral to do that. So we'll see how that plays out as we go through this problem. And then after that motion, we have it just traveling with some initial kinetic energy and on top of a hill, and then it goes over a rough patch and compresses a spring. So a lot of those things then are hallmarks of conservation of energy. So this would be a conservation of energy problem. All right, so let's go ahead and work through these. So the first one would be that we can get the velocity as a function of time on top of the hill would be equal to the integral of the acceleration, so c times t, and then dt. So that came from the one that was given. And so then this velocity as a function of time, because it starts from rest, there won't be any constant of integration, it'll be 0. So that's going to then be equal to ct squared over 2. And then the question is, well, you know, we want the speed, in order to do energy, we want the speed at x equals d. So how are we going to get the speed at x equals d if we don't know at what time it's at x equals d? So we need to know the time it is at x equals d. So what we need to do then is do this another derivative to get position as a function of time from our function for acceleration. So that'd be the integral of velocity dt. So the integral of ct squared over 2 dt. This is then going to be equal here. We're going to do this at some starting time, which is going to be equal to ct cubed. And then I divide by 3, and I already have a 2, so it would be ct cubed over 6. And then I'm going to evaluate that from t equals 0 to my final time, right? I'm just going to call that t1. And t1 is going to be the time that it's at x equals d. That's what I'm defining to be t1, is the time at which it reached x equals d. And that's actually what we want to find. And so then that's going to be equal to our displacement. Delta r is what I meant to write there. So that's going to be equal to our displacement, which is equal to d. So now I have this, which is c t1 cubed, because I'm just evaluating it, over 6 is equal to d. So the time, t1, the time it's at x equals d, is going to be equal to 6d over c, and then it'll be the cube root, which I write to the 1/3 power. So this is my important intermediate step, along with my previous velocity as a function of time. So the speed at x equals d is going to be equal to CT1 squared over 2, which is then going to be plugging this all in. It's just not going to look that pretty. I'm just going to write C over 2 times 6D over C, all to the 1/3 power. And so then that's going to be my speed. I'm going to just define that to be V1. That's my speed after that non-constant acceleration has been applied. So I'm going to go ahead and mark that in some way that I remember that's a key result. And then now what I'm going to do is, if we remember, that's going to be my speed going down this frictionless hill. So there's no more non-constant acceleration, goes over the rough patch and then compresses the spring. So my energy step, which I'll kind of resketch here, friction patch, spring, and then it starts here with that speed V1, which we had just found. So my initial energies, I'm going to have kinetic energy up here, right? This is all in my initial energy. And then the final will be when it's compressing the spring all the way. So my K initial plus my UG initial, because it's up on a hill of height h. It's not compressing the spring yet, and there's no friction patch yet that it's passed over. So those are my initial energies. And they're going to equal my final energies. And at the very end, it's at the bottom of the hill. So I'm calling that y equals 0. So there's no gravitational potential energy. It compresses the spring all the way. So I'm going to have my 1/2 k x squared. And then I'm also going to have no kinetic energy because it's at the maximum compression. And then let's not forget about my rough patch. I'm going to have my delta U internal. So that's going to be my general conservation of energy equation. Let's go ahead and plug things into it. Also remembering that what we're trying to find is the maximum compression of the spring. So we want to find X. So we go ahead and just work through this K1, K initial, be 1/2 m, and I'm just going to leave it as V1 squared now. So I just can write the messy thing in at the very end, but I don't need to include it just yet. And then plus mgh, h was given to us, that's the height of the hill, equals 1/2 k x squared, and again we want to find x, and then plus delta U internal, which is mu sub k times the normal force, it's level ground, so my normal force is just mg, times the path length, and that's going to be L, that was given to us as well. So I'm just going to then rearrange this and solve for x. So I'm going to have 1/2 m v1 squared plus mgh minus mu sub k mgl is equal to 1/2 k x squared. And at this point, it's just the algebra of going through all this. I like to cross off my 1/2s and then add 2's to everything that doesn't have a 1/2. And then I'm going to divide everything by k at the very end. So I end up with x is equal to the square root of m v1 squared plus 2 mgh minus 2 mu sub k mgl all over k. And then I need to remember to define v1 from above. So I'm just going to rewrite where v1 equals c over 2 times the quantity 6d over c to the 1/3, where that is my definition of v1. Box that whole thing, and this is my answer. So that is my answer to the combined concept question. Again, it's going to look messy sometimes, and that is totally okay. Two-step problem, although within that 1D portion, there was the additional integral, so kind of 2 1D motion steps. You can even think of it that way if you prefer. First, to get the speed as a function of time, but then also to find the time at which it reached x equals d, and then plugging that back into the speed. Okay, let me know if you have any questions.